Okay, so everyone. So today, again, I'm not going to teach new material, but I'm going to, not going to just repeat what I said. It's inefficient. So what I want to do is to give you examples, important examples of they are interesting by their own right. So in a sense, it's not really a repetition of what we did, but we'll redo things we did a little bit, and we'll use what we did. Use both the probabilistic method, both this construction, also factors or finding fields, codes, and fun. So everything. Relations. So the first example I want to talk about, in which we'll kind of see again the probabilistic method in action, and also construction using characters, is this notion of a tournament, or actually a paradoxical tournament. So what is that? Well, I need a small definition before we can actually say what that is. If you have a directed graph, you just write as a diagram, and you're looking at a vertex, G is a VE, vertex, subset. Then we say that X dominates B if all directed edges, there are directed edges from X to every vertex O, to every vertex in A. So for all A in A, you have the direct edge from X to A. So G is a B as usual. Right, so if you think of it as kind of players playing a game, you should. And this means, and you have an edge between, whether you have an edge from player X to player Y, X1, Y in the competition they made. And this means that X1, against all elements. There are no draws, and there is only one fight. One round. Okay.
Are you not allowing two
Right.
directions?
I won't. Yeah, I mean that's a general definition, but I won't allow it. If I would, then you could dominate each other. That's, yeah, it's an end. My end. And to give it a graph and X in the subset and a vertex in a subset. So that's actually going to be a really cool definition. So a diagram. Well, this hour or two we are going to only have the diagrams that I can cast. So a diagram is said to be K is an integer, a parameter, K paradoxical, if for every subset of the vertices of size K, there exists a vertex that dominates all the elements in A. So we will write that for saying that X dominates all the vertices K. For example, rock, paper, scissors is an example of a one paradoxical graph. There is no Magnus Carlsen here. Like, everyone is one by someone, you see. So this is a rock, paper, scissors. It's a one paradoxical graph because for every vertex, there is some vertex. So for every vertex in the set A, which is a singleton, there is some vertex, the one preceding it in this order, which dominates it. So it's slightly paradoxical, right? I mean, that's not so paradoxical, but it's slightly paradoxical. So this is a one paradoxical. Let's just like how a graph. it's not too paradoxical because these two, for example, any two it's symmetric, don't have someone that dominates both. Is this notion clear? Good. So let's just play with it a little bit before we're going to prove stuff. Let's try to construct two paradoxical graphs, diagrams. And kind of our goal would be to find the smallest one that we can, if it exists. Who knows? Maybe it's like too paradoxical. Okay. So I claim that you cannot do it with 6 vertices. And yesterday I had a short proof. And today when I forgot the iPad. So when I came to kind of redo it, I got a longer proof. So but anyway, I'll do it and see what happens. And I have the cheat sheet here to tell me how to do it. So okay, so let's see. Let's try. Okay. Let's try to construct two paradoxical graph on 6 vertices. Well, then 7 is C. Always. So what dominates? It means that you have an edge. So X, so a vertex dominates a set. If there is a directed edge from X to every vertex. For example, here, for every singleton, there is some vertex that has an edge. And actually, this example will illustrate it a bit more. So let's try. So, okay, if we had two vertices, just you cannot do it because there are no other vertex to dominate this. So you need at least 3 vertices. And you need someone that will dominate both of them. But that's what you have to do. And then notice that no one dominates, say, like 1 and 3. Because 2 cannot do it, regardless of how the edge here is going. So let's have a 4. Well, forced to have a 4th vertex that will dominate 1 and 3. Right, so someone should dominate 1 and 2, it's 3. One should dominate 3 and 2, it's going to be, it may be 4. Right, no, so it may be 4, but there is a way that someone can dominate this. What I want to do is to point out a couple for which you will have to add a new vertex. Right, so 3 and 4 in this case. 3 and 4, I mean, there are several ways of doing that. But 3 and 4, I mean, 1 and 2 cannot do it because actually they lose both of them. It is really bad. So you have to add a new vertex because 1 and 2 can do it to dominate this set, 3 and 4. Let's call it 5. Yes. Now, 5 and 4, someone needs to dominate them. It cannot be 1, 4. It cannot 5 and 4. It cannot be 1 because 1 was 4. 4, right. So 3. So you say 4 and 5 can be dominated by 2. So let me not do that. So let's go to 3 and 5. 5 and 3. 5 and 3, no one can dominate them because 2 loses to 3, 1 loses to 3, 4 loses to 3, but it loses to 5. So let's add a 6 here. Dominate 5 and 3, that's what we said, right? Good. And now I want to insist of not adding new vertices and fail. So let's see. There is I found that like a 3-line argument and then like a 6-1. So let's see. So 6 and 3, if I'm cheating here and looking at what I want. 6 and 3, look at 6 and 3 now. 2 cannot dominate them because of 3, also 1, 3. Also 5 because of 3, because of 6. 3 and 6 can only be dominated by 4. They can. I mean, potentially they could. But I just have to add this. Right, so the only one that can dominate these two without adding new vertices is 4. Try to make it as planar as possible. It won't do. And now you see that now the strategy is 4 got stronger now. So let's try to see who dominates like 4 and someone else. So my choice was 4 and 6. So let's see. And my claim is that only one can do it. So 4 and 6. So we are already. So my notes are not fine already this one. So let's see. Look at 6 and 4. One cannot dominate though. 2 can. 3 cannot. 5 can. So only 2. So we are kind of forced to do that. So hopefully only, let's see, hopefully 1 and 2 just get split. So let's look at 4 and 1 or 4 and 2. So let's see. 2 is not stronger. Let's look at 4 and 2. Let's see what happens. 4 and 2, 1 cannot dominate, it loses to 4. We cannot, it loses to 4. 5 can and 6 cannot. I really want to have only one option, so I don't have to. So we say that 5 can. It's 4, I have to be non-equivalent. Okay. Yeah, so okay, so I kind of lost it anyhow. Now, but now 5 got. I mean, in general, what's going to happen is that you need to kind of bypass the one that won you over, right? So like in operator scissor, you have to do like this. I mean, someone won over you, and you have to go behind their back. But in a two-way kind of, it's not more complicated. So can you help me? So like two got stronger now. So maybe let's look at 2 and 5. 2 and 3 are 1. 2 and 5. Looking in 2 and 5. So not 4, not 3, 5, 6, only 1, right? 5, 1. Now 1 gets stronger, so it makes sense to go to find a partner with him. You know. So let's do 1 and either 5 or 6. It's good to have 5 because you added this edge, so it doesn't count anymore. So 1 and 5. 1 and 5. So 4 doesn't win 1 and 5. Because 5 wins it. 2. 5 wins 2 also. 3. 5 is 3. 2 is 5. And 6. We can do 6. 6. Can we go 5 and 1? 1 and 6? Yeah, that's 1 and 6. So 1 and 6. So 2 cannot do it because of 1. 3 cannot do it because of 6. 4 can do it, maybe, yeah. And 5 cannot do it because of 1. So only 4.
Already. We did it already.
4. Yeah. 1 and 6. So not 1 and 6. Let's do 1 and maybe. Let's try 5. Yeah, I mean, I'm debating for who knows. We did 1 and 5? Let's see. Six over yeah, yes.
So
1, 3, we can go to 2 and 5 also. Yeah. 1, 3. 2 cannot be 1, 4.
the others.
1 and 3. 4 dominates 1 also. Yeah. Maybe 2 and 3? 2 and 3 is exactly 4. Yeah, maybe 2 fraction? 6. No, 6 doesn't win there. 5. 5, yeah. Also 5. Ah, okay. So the last thing we added was someone who won.
What about
2 and 3, I think that
5?
5, yeah. What about 5 and 6? 5 and 6? You have to repeat it.
One cannot be
That's the last thing, right? Just to make sure 1 cannot do it because of 6, 2 cannot do it because of 5, 3 cannot do it because of 4, 4 cannot do it because of 5. Ah, yeah. I had a free line.
This is
Right. Sorry, I mean, probably I got it wrong yesterday. Just sorry? I should just like yeah, I wrote it, but I wrote 6 3 1 4 6 4. I don't know. Let's do it with 7. The reason I'm doing this, so actually I'm doing this just to make sure the definition is clear. But the reason I'm going to do 7 is because I want you to appreciate what's going to happen next. So construction the on 7 rows. It's 2 paradoxical. Just call it 2 paradoxical. It's a very nice one. Not the construction that we do. So the construction is the following. Well, I need 7 vertices, so of course I'm going to take Z7. If this is the vertex set, 0, 1, 6. When I have addition in mind, we'll do 7. When you write this, you mean the group. We're going to just write a set. And I'm going to tell you what are the edges. So from vertex V is any number like that, we are going to have these edges. V plus 1, V plus 2, and V plus 4.
Yeah.
Yeah, it's weird, right? I mean, something weird happened there. It's a high dimensional. Right, so like formally for every V in this. So this is the edge. Right. So formally it's really symmetric. So for every vertex, we're going to have directed edge to 1, 2, and 4 ahead of you, module 7. Also, I should just say, I call it tournaments, and I didn't say what it is. When you do these things, when you want to prove the existence of Chapter graph, it doesn't hurt you to have more edges, right? Because the requirement is that there is someone there. I mean, adding an edge won't hurt an existing dominating vertex. Right. So, if you have a paradoxical graph, you also have a graph in which you have between every pair of vertices one edge in one direction. Just exactly one edge. And that's called a tournament. Because everyone are playing with everyone. So a tournament is just a diagram in which you have exactly edges to edges and no parallel edges. So in other words, and no settle. Because you don't lose yourself. In other words, there is an edge between every two pair of vertices. So that's why it's called, it doesn't really matter, but that's why it's called tournaments. Here I'm going to add, so for that, I mean that, okay. This is a tournament. I mean that you have the other direction, the edges of the other direction is actually in first order. It doesn't matter. So for this graph, for example, we look like this. I mean, it's enough to just draw from 0 because it's the same everywhere. So you have these edges, right? And then you cycle it. So the claim is that this is a two paradoxical graph. And the interesting thing is that, we didn't just draw edges. We can have some structure that we can argue on. Right? So yeah, minor structure, C7, 3 edges, not a big deal, but it's a general thing that if you want to analyze something, it has to have structure. Right? Unlike the probabilistic method, which you argue without the structure. But if you want to argue about a specific graph, I mean, you have to have a structure. Well, that's a structure. It's mild structure. So let's see. So let's say you give me 2 vertices. Actually, you can assume one of them is 0. Never mind. Let's say you give me 2 vertices, U and V, and I want to find some W that dominates U and V. By the way, know that W cannot be U or V by definition because there is no edge for vertices. Okay, so what do you mean find? So you give me U and V, and if there is such a W, then well, there is an edge from W to U. So this means that W is an edge. So maybe W plus D is U, where D is some element 1 to 4. Right? Saying that W points to U means that W is a number, W tells you is one of these elements. And because W needs to dominate V as well, it means that it should also satisfy the same W, maybe with a different edge label. If you want to prove that the existing W is dominant as well, it's equivalent. I mean, show that there is a W, a D, and an E in the different space. And actually, you don't need W, I mean, because you can write it without resorting to actually talking about W. Because if this holds, then definitely D minus U is, or U minus D is equal to V minus E. So if this holds, then that holds. But actually, if this holds, for some D and E, you can just install back W. Right? And if I'm telling you U and D, I tell you W. Right? So actually, it's enough, equivalently, to find a solution, given U and V, to find a solution to this equation in terms of D and E, where D and E are always. Right? So saying that there is someone that dominates them, essentially saying that this equation, where U and V are fixed, given, and D and E are variables that go over this set, this solution, this equation has a solution. You can push it a little bit more to three paradoxical graph when you need to work with Z19. Going to be present, we're going to do something else. Crazy. See that? Baby. It's not even a baby version of something. Baby itself, that's it. But it's still nice. I mean, I don't want to jump to the like super crazy stuff. I want to show you that even doing these examples. I mean, I gave it to my 8-year-old daughter. She was able to prove 6 doesn't exist with just step set. I don't know exactly how. And that she kind of said, that was hard. Maybe next year. So you want to solve for that, or equivalently, it's a field. You can move things around. Actually, it's enough that it's a group. It's a group. You can move things around, and really what you want is so you're given U and V, so essentially you're given this difference, and you want to find D and E that satisfies. Right. Yeah, probably. Now, the point is that U and V, this can range over everything in Z7. If U and V is a singleton, it's also can be zero, everything. So it's enough to show that these can range over everything. Right? So it's enough to show that this set minus itself, namely element by element, is all of Z7. And that's true. Because 1, 2, 4 minus 1, 2, 4. We talked a little bit about these things where you subtract or add sets to themselves. So right, so 1 minus 1 is 0. Of course, it is only have one vertex. It's the same. 1 minus 2 is minus 1, which is 6, if you want to go positive. 1 minus 4 is minus 3, which is 4. 2 minus 1 is 1. 2 minus 2 is 0, we have it already. 2 minus 4 is minus 2, 5 over 7. 4 minus 1 is 3. And 4 minus 2 is 2. And plus enough. Okay, so that's why this is a 2 paradoxical. Now, it's not clear that there is by the name, 3 paradoxical. I mean, it's kind of getting harder because you need to bypass those who want you, but the arity gets larger. You have many bosses, and you need to go over all of them in a sense. I don't know, definitely doing it by hand is not going to happen. You need a global single thing. I think it was a question, like, I don't know what K paradoxical can exist for. Maybe it's really new or something. For some larger K, it wasn't there. And then, who proved that they exist? Prof. Paradox. Yeah. He cheated, he used the probabilistic method. So we're going to do that. We can say again the probabilistic method. But then we're also going to construct such a graph, and that's amazingly beautiful. So, but let's move of the existence of k paradoxical terms. Okay. Again, the proof is going to be disappointing. It's going to give you absolutely no idea of how this graph looks like. But on the other hand, it's going to show you that essentially all graphs. So it's, if all graphs have this property, maybe you shouldn't expect structure, like everything works. Structure only reflects about yourself as a person who can study graph, not about the graphs. Okay, so how would you do it using probabilistic? How would you start? What's going to be the distribution? Right. So we're going to have, so you can say uniform over all tournaments. One thing, it's the same thing as what I'm going to say, but I have a more local. And between every two vertices, we're going to have an edge oriented this way or that way, committee 1/2, same distribution. But it's easier for me to think about. So, right, so consider a uniformly chosen tournament over n vertices. So we're going to have some bounds. So if you want to construct a K paradoxical tournament, for a large enough n, we'll be able to do this. Okay, so we don't know yet what n is. In this distribution, K doesn't even exist, right? So we just chose an n. In a couple of minutes, you'll see that n is up to k squared times 2 to the k, at least, never mind. But I'm just looking at uniformly tournaments over that size. And now, what should I do now? What's the recipe? I have it. Good. Sorry. It's too hard now for some reason. In general, you need to break down your problems and then to have a union bound.
How many subsets? K subsets.
Right. Good. So I'm going to fix a set A, size K. I'm going to handle it and then again fixing one. Okay. So now, what's the probability that a specific x, like I chose an x, what's the probability that x is fine for it? Everything's good. Exactly. Right? Because every edge between x and every element in A is oriented either this way or that way, so we really have it's oriented in the right way. The independence so it's minus k. So that's for a fixed x. Or the fixed A. And so the probability that every x fails, I don't want that one, that every x fails, I did that, is what? Right, so that's a probability that the specific x will fail. Oh, okay, so that's probability the exact, so that actually, for now, that's exactly the probability that x will fail. And different x's are independent. Like, and how many x's which I actually should count, really? N minus k. You should think n, but it's not n, because the vertices within A cannot dominate A. So only those vertices outside of A, implicitly says that you want to dominate x's outside of A. So you have this probability for specific x to fail dominating A. That's okay, and then because of the independent, just sampled from two distinct vertices, so all distinct vertices to A, you have this product.
What happens if you have like a directed in A is then each vertex
It doesn't dominate itself.
yeah.
Right, that's yeah. It's a technicality, I agree. But it's important for other one. Okay. I don't mind that would be an inequality, by the way, but that's just funny. Yes.
Must be an edge between.
Yes. Right. So in a tournament, you have between every two vertices, you have an edge, oriented either this or that way. And you can think of also non-dominant paradoxical graphs. That's only considered dominance, because if I want to prove that they exist, I better use everything I have, all edges. Okay. So what's the kind of equation I care about? So that's for a fixed state. That's a probability that my graph will fail for a fixed state. So what should I do now? Exactly. So I'm going to take the union bound. This is the number of ways to choose a set, number of A's I have to worry about. And if I multiply by this by the probability that a specific A fails, that's the probability that the graph is not a tournament, not a k-tournament. So the probability that the sample A, the sample G is not a paradoxical is bounded. It is a bound. It's bounded by that. And the key point is, what do I want from that quantity? I want it to be small. Because that's the bound of probability of something bad to happen. So, smaller than 1. I mean, you can, once it's smaller than 1, and that's the probability signal for the action, it says that there exists a graph, which is a paradox. If it's smaller than half, which is essentially the same price as statistically, means at least half of the graph are paradoxical. And for the same price, you can make this very small anyhow. You don't have to write 1 here, you can write 1 or poly n or something, still really. So actually, most graph, by the same reason, replacing the 1 with something smaller, the same, and we know that most graphs will be paradoxical. It's crazy, but it seems it's paradoxical. Everything is paradoxical, so it's not really paradoxical. Yeah, it's, right. Okay. Okay, so for me, it's just a calculation, but then just do it. So I want this. This is not an inequality that falls, right? I want that to happen. That is enough to bound this in and this left-hand side and show it's also smaller than 1. And I'm just going to use like this bound. So n to the k is our easy bound, and then to choose k, you can be slightly more. The constant will be a bit better, but doesn't matter. Okay, 1 minus something, it's always bounded by e minus that something. Right, so I'm using here plus or minus as well. Okay. Right, but not just approximation, it's an upper bound. So this is no upper bound. Because I'm not divided by the k factorial, I'm not reducing any minus 1. Or combinatorially, this is a choose k things with repetition, and this k without repetition. And of course, I have the n minus k, yes? So, since that's an upper bound on the left hand side, it's still enough to have this. I want this to happen. And okay, from here, let's just take this to the other side and take a look. 1. K then is at most minus k and minus k. I just the here, and then this means once I multiply by 2 to the k, then other k, you have the n, so it suffices there. Right? Demanding that is the same as demanding those. 2 to the k, scalar n, plus k. If you multiply by 2 to the k, then so the point here, this is like, this k is nothing. Multiply by 2 to the k times n. So I can, in the first time you do it, you just ignore it and see what happens. But just to be like completely accurate, I'm just going to kind of swallow it here and say, well, that's enough. Because I'm replacing it by something like that. It's still this will imply that. And then the only thing you kind of need to know, I mean, you have like n over ln n larger than 2 to the k plus 1 times k. Then you ask yourself, well, what's the n I should choose? Because if I choose exactly that, it's not going to work. So essentially, what you have to choose is like you should choose an n which is like twice this ln of itself. Right? So this is another rule that you have to know. It's good to know. If you want x log x or x ln x or whatever, so x over ln x be at least y. Then you kind of sense that you should be y ln y. No way, but it's not enough. You need like maybe 2 ln. So you need x to be 2 y ln. 2 just to you can replace 2 by a smaller constant, but not 1. Because if you have a 1, you'll fail. Because you'll have a y ln y over ln, which is slightly larger than y. Anyway, it's easy to check. I mean, if you want this is what you want. Just take x to be slightly larger than what you think. And so in our case, this means that it's enough to take. Now it's enough. Because I need. Now it's enough to take n, which is this times the ln of itself. The ln of this is essentially k. So up to some constant, which I remember, it's k squared times 2k. And this is some constant. Maybe 4. Because you have the 2 constants here and there's another constant here. It doesn't matter. Only 4 should work. So overall, what happened here is that we found it at the end. But if you take a tournament of a random tournament of size n, with high probability, really, it will be a k paradoxical graph as long as k satisfies that. Maybe with equality. I mean, with equality, definitely, but we should think with this other direction.